you this. What do you mean by speed of reaction or kinetics? How is it different than the thermodynamics? Are they related, not related? What do you think? Anyone? We did that last time, right?
How are what related? I'm so sorry.
So our speed of reaction and the thermodynamic, which is the reaction energy, are they related? So for what you have studied. So we went through that aspect where we mentioned that the reaction energy is different than the activation energy. Activation energy is where we are talking about the kinetics, and reaction energy is where we are talking about the thermodynamics aspect. So having low or high activation energy may not be connected with the reaction energy. Although there is a postulate, we call it a Hammond's postulate. This is what you're going to study if you are taking advanced physical chemistry, not in this course, but then there are cases where you can make the reaction more and more exothermic and the barrier will start to fall. But then that's a different aspect. It's a Hammond's postulate, not in this one. For now, you have to think about the thermodynamics as a different component than the kinetics in any reaction. Okay. Now here in this case, we were looking at instantaneous rate. We were looking at the initial rate. Now so this is a graphical method. Now, what if you were given the data for each point? Let me show you that one. So this is the data. Now this has been taken directly from your book. Now, when you look at the speed of the reaction, so you can see what was the concentration of a particular, your starting compound, and you can see that starting compound is going down. The concentration is going down with the time. And when you find the difference between every point, you can see that difference in concentration divided by time. So that would be C4H9 Cl divided by time. That's what we are trying to find here, right? So just like when you are trying to find the speed between the 2 points, just like here, you did the same thing. You found the change in distance over the change in time, and you found the speed of your car. It's exactly in the same way. You are looking at the final point minus the initial point. So final concentration minus the initial concentration, and the final time minus the initial time. That's going to give you the speed of reaction. Okay. Now, do you see anything interesting over here going on? So when I'm writing these boxes, I'm referring to average reaction rate. I am talking about the instantaneous reaction rate. So for the first entry that you see, it is between these 2 points. The second entry is between these 2 points. The third entry is between these 2 points. So I'm looking at the instantaneous rate. So just like when you see over here, for every point, you can make a line, and then you can find the slope of that line, and you can get that instantaneous speed. How about here? This is in form of numbers that you are seeing. Now, did you notice something interesting going on? Isn't it that the rate of reaction on a curve should be constant if it was a straight line? So look at this one. If you had C4H9Cl, the concentration of your substance falling down in a linear way, if it was linear, then the rate over here the rate over here and the rate over here will be identical. Why? Because the slope along that straight line is going to be the same slope all over the line. But that's what not you are seeing. You are seeing a curve. And on the curve, you are going to see the change in slope at every point, right? So when you make a line over here, so if you're looking at this point, look at the tangent and slope. When I'm looking at this point, look at the tangent and slope. When I'm looking at this point, look at the tangent and slope. So every point will have a different slope, right? That means every point will have a different rate. And you can see that, right? So initially, the rate was 1.9 10 to the power negative 4. By the time you reach to the low concentration, the rate has fallen down to 0.56 10 to the power negative 4. Can you tell me why is that? Why is rate falling down in that way? Why does not rate follow the linear pattern?
Well, Professor, it's not necessarily a straight slope.
Compared to the top, which is 1.9 10 to the 4, the bottom one is 4 times slower, roughly 4 times slower. So what is happening inside your flask? So rate of reaction is falling down. This is, you can see that at every point it is falling down. Why?
Because there's less and less reactant while there are more products within the same flask.
Absolutely. So you are not changing the volume. Volume of your reaction stays the same, number one. So molarity, you are not changing the molarity in terms of your solvent. It stays the same. Now, in terms of your reactant, you are decreasing the concentration of reactant. So you are, in effect, you are decreasing the molarity. And we know that if you decrease the concentration, that means you are decreasing the chances of collision between the reactants. When you decrease the chance of collision, you will be decreasing the reaction rate. This is what you are seeing here, right? So this reflects the lower concentration of your starting compound, as you mentioned. And this is the reason why we want to study our reaction in the initial states only. We don't want to study our reaction here. We want to study what is happening over here, right? We want to see our reaction with a full concentration of reactants instead of having partial concentration of reactants. We don't want to do that. We want to look at the top initial rates. Okay, so you can analyze the data in that particular form. So first of all, you saw the graphical data. Now you are seeing the data in form of the table. Okay, now I can write this rate as I mentioned over here. D stands for change in concentration of your reactant over the change in time. But now you can see that in the denominator, 50 minus 0 is a positive quantity. We don't need to worry about that. But in the numerator, you are subtracting a bigger quantity from the smaller quantity. So this has to be negative. Now, if I write down the rate of this reaction, that's going to be change in concentration of my reactant. But then the rate of this reaction in terms of change in concentration of reactant should also reflect the change in concentration of product, because I am using up my reactant, but then at the same time, I am also generating my product, right? So they will go hand in hand. So this rate is exactly equals to the rate of formation of my product. And see, that one is positive. Why is it positive? Because you are generating more and more product. So final concentration is always going to be greater than the initial concentration. That's why that sign is always positive. So far, so good?
Can you repeat that, Professor? Just straight.
Okay. Okay. Here in this case, your final concentration of reactant is smaller than your initial concentration because you're using up your reactant. That's why the negative sign will appear. But if you look at the rate for the formation of product, the final concentration will be always greater than the initial concentration. So that sign will be always positive.
Got it.
Now, when we are thinking about the rates, stoichiometry, the reaction stoichiometry, also plays a very vital role. Now, what do I mean by that? Suppose if you have a reaction, let me put a reaction over here for you. Let me take one generic equation and then we can build on that. Suppose you have A moles with a small case A that actually tells you the coefficient of reactant A reacting with a B moles, giving you C moles of your product. In this case, if I write down the rate, I can simply write as that. That means how much A is being used in a given time. That should also be equals to how much B is being used over the time. And that should be also equals to how much C is being produced over the time. Only problem is that this equation does not reflect the reaction stoichiometry. See, we have A, B, and C. I'm using the different moles. So when I balance my chemical equation, that should reflect somewhere in my rate equation. And how does it do that? For the first one, it is 1 over A. For the second one, it is, okay, I don't have space to write that. So I'm going to move my negative sign a little bit here. 1 over B. And the third one is 1 over C. So you need to divide your coefficient. So you need to divide the rate by that coefficient. And that will give you the rate in terms of A, rate in terms of B, and rate in terms of C. Now, let's apply this in one of the scenarios. Now, suppose ozone gas. We know ozone gas is unstable, and it can decompose into O2 gas. Okay, first of all, balance this equation. Second, find me the rate equation. The way I showed you the rate equation before, find me the rate equation for this and tell me how it looks like. And I'll give you a minute to do that. Shouldn't be taking more. Anyone so far? How would you balance this equation?
I mean, 203 and then 3O2.
Okay. Okay.
And then it's hard to like write what the rate would be, but it would be -1/2 the change in O3
Mm-hmm.
over change in time equals positive 1/3 change in O2 over change in time.
Very good. Very good. So basically I can write rate equals to -1/2 change in ozone concentration over time. That should be exactly equals to positive 1/3 change in oxygen concentration over time. That should be exactly the same. So far, so good.
Professor, the DO3 over DT is change in concentration, we said?
Yes. So that the parentheses reflect that. Now, do we have any doubts so far before I go to the next topic? Okay. So the next one is about the order of reaction. Now let me give you one example over here. Let's start with a simple generic equation where I have A plus B giving you C. Now, as I mentioned, that rate always depend on the initial concentration, number one, on the reactants. It doesn't depend on the products, right? So I can write my rate equals to the concentration of my reactants like that. Now, the stoichiometry is also going to play a role, but not the way you saw it here. Suppose if it is A and if this is B. Should I be writing A over here and B over here? Answer is no. You cannot simply write this A and this B is quite different than this A and this B. So this one actually tells you how many moles of A and how many moles of B are involved in a particular reaction. That's a balanced equation. This A and B tells you how many moles of that particular substance are involved in a rate limiting step. So I'm defining a rate limiting step now. How many of you know what a rate limiting step is? In many books, it will be written as RLS, and in many books, it will be written as RDS, rate determining step. Okay, now what exactly is that? Now let me give you one example. How many of you go to gym for running, or how many of you go for a running track?
Yes.
So do you guys go for a workout?
Yeah.
Okay, many of you do that, right? So can you tell me who is the fastest runner in the world? 100-meter sprint? Usain Bolt, right? So, exactly. So Usain Bolt is the fastest runner, right? Now, suppose we have 3 runners. One of them is Usain Bolt, and then I'll just say Usain Bolt. Then we have second runner. Well, probably that's going to be me. And then we have a third runner. Let's put a third runner. How about a third runner? Okay, so we have 3 runners on a running track, and they all are moving in this direction, right? So this is Usain Bolt. This is DV. That is me. Who wants to take the third point? Who wants to run in
That's
that race?
me.
Oh, you want to run that? Okay. So I'll put Kimberly Steele in that. Okay. So suppose we three are running on a running track. Now, can you tell me? Now, I'll tell you, I'm not a good runner. I can tell you that. Okay. Now tell me, who is going to be first, who is going to be second, and who is going to be third in this race? 100-meter sprint.
First, clearly.
Does everybody start at the same time?
Yeah, everyone starts at the same time. Exactly.
I mean,
Okay, so Usain Bolt is one, Kimberly Steele comes second, and I go third. Probably I won't be able to finish the race. Okay, so we got these three runners. Now suppose I do something interesting here. How about in the next experiment, I tie all three runners. Now what's going to happen? If I tie them together, what will happen? What would you expect in that race? First of all,
we all
there is not,
finished.
they all finish at the same time. Exactly. Now, Usain Bolt, who was the fastest runner, say, for example, he finishes the race individually, 100 meters in 9 seconds. Suppose you do it in 10 seconds. And suppose I do it in 50 seconds. Now, when I tie them together, can Usain Bolt make all three of us reach in 9 seconds?
No.
No. Now, think about it. Two runners are fast. So who is going to control the speed of these three runners together?
It would probably be you being the limiting factor here.
Exactly. So I'm going to decide how fast or how slow we all three will be running together. Think about the reaction in the same way. Now, although we are writing the equation like this, that's the final step, initial reaction, initial reactant, and then we have final product. But then in the mechanism, we don't know what is going on. It may be 2 steps, it may be 4 steps involved in a particular reaction. Now, in that, which of them is the slowest step is going to control the reaction. And these numbers, the A and B, are actually giving you the concentration of reactants in the slowest step, right? And they are going to determine the rate of reaction. That's why we call it as a rate limiting step. Now, when I look at this equation, this A and this B, we call it as order of reaction. In A, order of reaction in B. So A is order of reaction in A, B is order of reaction in B. I'm referring to the green numbers. I'm not referring to the blue numbers. They are different. Okay. And then A plus B will give you the overall order of the reaction. Now, how do we find this overall order or order of reaction in A and B? Let's look at one example. Let me paste one table, and then that's going to help you.
Professor.
Yes.
So the big A's were the moles. Is that what you were saying? Big A and
No.
big A and B.
Okay, so big A is the identity of your reactant. So I'm talking of the concentration of A and concentration of B. So concentration is expressed in moles per liter, not in moles. Yeah. So those square brackets, that means we are talking in moles per liter. We are talking about the concentration in terms of moles per, not in moles per liter. Okay. So here is an experiment that is given to you. And if I simply write rate equals to K, which is the constant, concentration of A, concentration of B, and A and B are the order of reaction in A and B components. Now, see what is happening. When I keep my concentration of B constant, so that means this concentration is not affecting my rate. Now see what is happening. When I double the concentration of A, is there any change in B, in the rate? Do you see any change in rate?
No.
No, there is no change. Very good. So if there is no change by increasing or decreasing the concentration of A, that means the order of reaction in A is 0. That means it is not affecting my reaction. Let's see what happens with B. Now, in the second experiment, I'm keeping the concentration of A constant, but now I'm doubling the concentration of B. I'm increasing by 2 times. Do you see the change in B in the reaction rate?
Yes.
So that's going to be 1, because if you increase by 2 times, you are getting the increase in the rate by 2 times. If you increase it by 3 times, you are going to see increase in 3 times. So B has to be 1. Why? Now let's see the final rate. That's going to be K B raised to 1. Now, this one will explain why you are only seeing the rate jumping by 1 time every. So as I mentioned, you increase the concentration of A by 1 time, I mean B by 1 time. So going from 1 to